Okay, this lecture is going to be an overview of Earth system science. So these are things that we will, in many cases, come back to at different points in the course, different aspects here. And this lecture is based on a reading. This is pages 1 through 17 of a book called Earth System Science. A very short introduction. And by author Tim Lenton. Okay, so Earth system science. Okay, we've talked about system science so far. Earth system science, the goal, it seeks to understand the whole planet Earth as a system. So that means that can be different time scales. It could be the entire age of the Earth, but also the sort of decadal or 100-year sort of 10 to 100 year timescales. We'll talk a little bit later about how differences, depending on the time scale, different processes are important. Earth system science is concerned with, among other things, particularly for the shorter time scales, human influences. And aims to not only understand what's happened in the past, but use that to project future states. So that's always a goal, or often for a lot of models, that's a goal. If we get models going that replicate what we've seen in the past, and we have more confidence that there's some accuracy when we project things into the future. So Earth system science is very interdisciplinary. There are aspects of it that are involving chemistry, physics, biology, atmospheric science, solid earth science, geology. It's a very broad set of things that come under the umbrella of Earth system science. So one of the key ideas in Earth science is what differentiates Earth from other planets. So we can use other planets as sort of examples of other ways that life can go, or that a planet's evolution can go. And I just kind of gave it away there that life, this is sort of a key aspect of Earth system science. Life is seen to differentiate Earth from other planets. Okay. This isn't really. This kind of comes out of. I'll be describing in this lecture the evidence for this, which is very clear. It's not really a hypothesis. It's at this point, it's kind of about as clear as could be. So one key difference between Earth and other planets is the chemistry of Earth's atmosphere. So just write chemistry of Earth's atmosphere reflects this. So this being this comment about life. So we see evidence of life looking at the atmosphere of our planet, particularly in comparison with other planets. So we find in our atmosphere many highly reactive gases. Like oxygen and methane. These are things that just don't tend to just exist all by themselves without being constantly generated. And this mixture of the atmospheric mixture is both a product, so it results from life, and it allows for life. We wouldn't be here without oxygen, right? For example. And life, it's, the photosynthesis is generating that oxygen. So that's a process from life forms. So our atmosphere is not dominated by carbon dioxide like some other planets. For example, our near neighbors Venus and Mars. So one of the reading talks about how a NASA scientist was given the task of how do we determine if there's life on Mars, and they were thinking about sending some spaceships there, and his conclusion was the best way to determine if there's life on Mars. We don't need to go there. We could just point our telescopes and look at the atmospheric composition. So the atmosphere is a huge, and that's still going on today. They found methane there, and that's this big question of does that indicate life, or maybe there's some other ways to generate a little bit of methane? There's not a lot, but there's a little. Okay, so let's look at some. We'll look at a couple of sort of key parts of the Earth system, and this one will just define it as a puzzle, or systems puzzle number 1, and that's just my name for it. It's not an official puzzle, but this puzzle is the question of the stability of Earth's temperature. So it's known that stars get brighter, or they get stronger over time. So 4.5 billion years ago, it's clear that the sun was around 30% less luminous. And that means less energy arriving at the Earth, and calculations of the temperature that would result from that would be around 30 degrees Celsius cooler than present. In other words, the Earth would have been frozen. Frozen, except there are greenhouse gases, notably CO2. So greenhouse gas, just a reminder in case you didn't know that, greenhouse gas CO2 kept things warmer. So there's quite a bit of CO2 in the early days on the planet, much like there is a lot of CO2 on Venus and Mars. And one piece of evidence we have that the Earth wasn't frozen at that time is there's sedimentary rocks as old as 3.8 billion years. So these rocks formed in oceans. So it's clear there were oceans almost 4 billion years ago. So it wasn't a frozen planet at that time, clearly. So at first this was a puzzle. People didn't know why the Earth was not an ice, not even, why it wasn't a frozen ball this long ago. And then they realized, CO2 would explain it. Okay, but given the fact that the sun has been gradually increasing in brightness, solar influx has steadily increased. And we're still a habitable planet. So that's the question, that's the puzzle. Why? Okay. And the answer appears to be that CO2 has steadily decreased over time, keeping temperature within a life-supporting range. And this is part of the motivation for the Daisy World model, where if you look at sort of the temperature, if you look at a plot of time versus temperature on a sort of a dead planet, you would expect it to just be gradually increasing. However, temperature's done something more like that so far. So it's stayed within a range that's, let's illustrate this dead planet. And there's variations on this, and I'll talk about some of that in a moment. But overall, so maybe it's doing a little bit of that here and there. But dead planet versus what happened. Okay. So the main hypothesis that addresses this is called the Gaia hypothesis. And this was developed in the late 1960s and early 1970s. And the basic idea is that the Earth systems, multiple systems here, regulate the atmosphere and climate in a habitable state. And this hypothesis is named after the Greek goddess, the Greek earth goddess, Gaia. And so what this means, like all systems, this means the earth is not just a sum of its parts. It's kind of like the anthill. Somehow the parts work together to form something much more significant than the individual ants. And this was not meant, if you Google Gaia hypothesis, you'll see it's been popularized in some communities as indicating like a sort of an intelligent, like a actual consciousness of the planet. For example, like in the movie Avatar. But that's not the way that it was intended originally. It's as we've seen with other systems that involve not necessarily conscious things, that systems have feedbacks and can maintain themselves without what we know of as consciousness. At least, science can't really prove that's not happening, but it falls out of the realm of something that can be tested or what we can really think of as science. So the Gaia hypothesis basically says that the stability we've just discussed of the planetary environment for life, that stability results from a combination of positive and negative feedback loops. And we'll look at a couple of those examples of that next. So we'll start with feedback loop example number 1, which is silicate weathering. So that's basically, silicates are the type of minerals or rocks. So and weathering is the process of the breakdown of those at the surface of the earth. So so silicate weathering combined with the formation of carbonate, so that's like limestone. So the dissolving of typical rocks that are found around the Earth's surface, and the formation of carbonates in the oceans generates a feedback loop that's critically important for life on this planet. So this process removes CO2 from the atmosphere and oceans. So we'll talk about this in greater detail later. But gases that are in the atmosphere, they also end up dissolved in the ocean as well. So what happens here is that the weathered atoms from rocks, so atoms that were in rocks, but they got liberated, particularly calcium being the most important here. So calcium is found in minerals, but it ends up through this weathering process dissolved in water and in rivers, ending up in the ocean. Weathered atoms from rocks combine with carbon dioxide to make limestone. So this is basically, there's different ways this happened, but one of them is just the shells. If you think about going to the particularly warm areas, beaches near the ocean, there's all these shells. Those are limestone, or they're not limestone. They're made of this mineral, calcite. And when those shells and other marine bits pile up on the ocean floor, they turn into limestone eventually. So we're looking kind of at a long-term process here. There's a series of steps by which shells and carbonate end up as a rock. We're skipping over, but the bottom line is that this combination of wearing away the Earth's surface, dissolving stuff into the water, combining it with carbon dioxide in the atmosphere, it puts CO2 basically into the ground. And this process, like most chemical, or maybe all chemical reactions, occurs faster at higher temperatures. So we find a lot more, we find warmer oceans up to a point. Think of coral reefs. Those are made almost entirely out of calcium carbonate. These are things that we find more often in warmer places. So this process happens faster when the temperature is higher. And so what I'd like you to do next is pause the video and see if you can draw a causal loop diagram that illustrates the feedback based on these facts that we've just listed here. Okay. So what we've said is that weathering affects the carbon dioxide levels in the atmosphere. So is this a positive or negative feedback? So if we have more weathering, we have more of this carbonate formed, so that the level of carbon dioxide in the atmosphere decreases. So more weathering, less CO2 in the atmosphere. So this is a negative. And the less carbon dioxide in the atmosphere, via the greenhouse effect. So we could add the greenhouse effect here, but I'm going to skip to just planet temperature. Okay, so temperature. Okay, so less CO2 in the atmosphere means lower temperature. So that's a positive. more CO2 would mean higher planetary temperature. That's more what we're thinking about these days for global warming issues. Okay. And we just talked about how silicate weathering is faster at higher temperatures. So if temperatures go up, there'll be more weathering. So that's another positive. And so we can, the rule here being, we multiply these together. So a 1 times negative 1 would be a negative 1. So this is a negative feedback. So what that means, negative feedback, certainly not negative in the sense of whether it's good for life on Earth. This is a major life-supporting process, but negative in the sense that it's a stabilizing feedback. So it works to stabilize the temperature on the planet. So just you remember this, but stabilizing. So it's also worth noting that you might be wondering, well, if we just keep using up the CO2, aren't we going to run out? And so take note that CO2 is steadily added to the atmosphere from volcanic eruptions. And another thing to note is that plants create acidic environments that enhance weathering. Speed it up. So once land plants evolved, this process accelerated the rate that this feedback loop could work. So this doesn't completely, this alone doesn't completely explain the temperature regulation on the planet, but it's a major component of that system. All right, let's look at a second important feedback loop. This is what's known as snowball Earth. Okay, and the basic idea here is that climate modelers realized that Earth's climate can tip into a completely frozen state. And the feedback here would be related to albedo. So if, and recall that so let's just say due to albedo. And just recall that a mirror would be 100% albedo. I sometimes forget what high albedo means. Black would be 0%. Okay, so the idea here is that if there's more ice on the Earth's surface, that's whiter, it's more reflective, higher albedo. So more ice, more albedo, that's positive. And the more of the sun's light that's reflected away from the Earth, the lower the temperature will be. So that's a negative. More albedo, lower temperature. And the lower the temperature, the more the ice. So that's another negative. Temperature goes down, ice goes up. So this is a positive feedback, so -1 times -1 times 1, positive. So this is a positive feedback. And modeling of, we know basic things about, the solar influx and the albedo of ice, and characteristics of the atmospheres. And the models suggest that the Earth could remain stable in a frozen state. So the question really, and this has happened. So before we get to the question, there's strong evidence in the geologic record for this. For example, there's something called drop stones. So when you have icebergs, sometimes they've been scraping along, ice in glaciers is scraping along the bottom of the bottom of a glacier will pick up rocks as it's eroding away, and those rocks get stuck in the ice. And when those icebergs float away into the ocean and they start to melt, those rocks fall out and they land in the bottom of the ocean. And so there's periods in time where sedimentary rocks that were formed in near the equator have these drop stones. This is one particularly kind of it's the equator, just one of those. This is one really clear evidence that there was a lot of ice at particular points in geologic past on the Earth, even down in the equatorial range, which would never occur in a climate like we have today. The icebergs just don't get that far. And there's also all kinds of other evidence in the isotope record, for example, for the snowball Earth state. So the question is, how is this escaped? How does the Earth get out of the snowball Earth state? And the key to that is that maybe take a moment. I've given you some clues earlier in this lecture that you have information about how this could happen. But I don't blame you if you don't think of it, because it took Earth scientists a while to figure this out themselves. But the bottom line is that that CO2 builds up. So the volcanoes I mentioned, volcanoes keep erupting even if they're under ice, as we've seen, for example, in Iceland in recent past. Volcanoes are releasing CO2 steadily, and that CO2 builds up until the greenhouse effect becomes so strong that the ice melts. So to large greenhouse effect. And so many of these things are going to talk about later in the class, like the greenhouse effect. Okay, so at the same time, so CO2 is building up, but also remember this cycle we had a few slides back, right? Weathering typically is removing the CO2, but weathering during snowball Earth basically comes to a halt. So at the same time that the volcanoes are putting in more CO2, weathering and carbonate formation, we'll just say are subdued or slow dramatically. Okay, so we talked about carbonate forming in warm places, but if the Earth is in a frozen from pole to equator, it's not going to be warm enough to form carbonates. So that's a lot of CO2 coming in, no CO2 coming out of the atmosphere. Eventually, the atmosphere becomes so carbon dioxide rich that it melts the ice. And then, so like all positive feedback, like all positive feedback loops, this one works in both directions. They all do. Okay, so this same feedback that we wrote out for the Earth, heading into a frozen state, works in the other direction. So once the ice starts to melt, so now we have, think of this as, okay, less ice means lower albedo, which means higher temperature. The higher temperature means even less ice. Okay, so the feedback goes the other way until the ice is completely gone. And that's, by the way, that's the same direction that that's occurring right now with human, anthropogenic global warming on a short time scale. Melting of the ice caps, lowering the albedo, which is accelerating the warming, which is accelerating the ice melting and so forth. So this puts, so let's just get this written out. So works in both directions. So exit from snowball is what we call a hothouse. So you suddenly have changed the albedo dramatically lower, and you still have all this carbon dioxide in the atmosphere, so it gets super hot really fast. And it's called a hothouse climate. And that's going to dramatically increase weathering, right? And carbonate formation. Carbonates can form everywhere at that point on the planet, probably. And so the Earth can kind of alternate in and out of snowball hothouse states, and there's evidence for this, particularly around 500 million years ago, which was right before what's known as the Cambrian explosion. So there's theories that that's not an accident. So the Cambrian explosion is when the first sort of not life forms that weren't basically just like algae and stuff like that, like, animals basically showed up suddenly right after a series of these, hot, cold events. So the idea is maybe that somehow that climate chaos created an environment where life, as we know it, could emerge. Or not life as we know it, but the sort of the life forms that the complex life forms like us came out of ultimately. And there hasn't been a snowball Earth state since then. So perhaps the life, like land plants, for example, that's come since then has helped sort of stabilize the climate. I'm speculating there, but it seems likely. Okay, so we'll wrap up with by talking about the boundaries of the Earth system. So anytime you're talking about a system, it's one of the first things you would want to do is consider, what's going to be in the system and what's going to be outside of the system. And so the upper boundary is pretty straightforward. It's the top of the atmosphere. And interestingly, there's different lower boundaries depending on the time scale that is being talked about. So for the long term, like we've been talking about, the two examples of snowball Earth and the carbon dioxide levels, over those sort of billion-year timescales, we include volcanic outgassing. So that's the gases coming out of volcanoes, the formation of sediments, so the things that we've been talking about. If you think about I'll just do the sun getting brighter, that is a long-term process. Right, yeah. The fossil fuels that humans are burning right now, right? Those formed over tens, hundreds of millions of years. That they're sediments. They came from sediments. So those sorts of things that are interesting for the long-term carbon cycle. So this includes recycling of materials through subduction. So in introductory geology classes like EAS 106, think about the subducting ocean plate. This is an arc. So sediments are deposited in the bottom of the ocean. Those sediments are carried down, and some of those gases and materials end up coming back out through volcanoes. So that there's a long-term recycling that takes, tens to hundreds of millions of years to occur. So if we're thinking about this long-term systems, the lower boundary, we definitely want to go down this deep, right? At a minimum, that boundary would be generally the upper around 100 kilometers of Earth. Let's put. Okay, there's probably some stuff goes deeper, and some volcanoes are getting stuff from significantly lower, but most of the processes probably that are relevant for the long-term Earth system are kind of in the upper 100 kilometers or so. And so by long-term, we're talking about 1 million plus, million or more year time scale. So these things we've just been talking about are too slow to affect and to be really relevant for anthropogenic climate change. The oceans just can't keep up with the amount of carbon dioxide we are putting into the atmosphere, and it's being absorbed in the ocean. So Earth system scientists also talk about the short-term, what they call the short-term cycle. So it could be the short-term carbon cycle or the short-term Earth system. So this, in this case, when we're considering the boundaries, we would include the biosphere, the oceans, the atmosphere. But we're not going to go very far deep into the Earth. So the lower boundary would be Earth's surface. I'll just say, just kind of leave that loosely defined. And here, short term, we're talking about sort of a century scale. Which is what's relevant for climate change studies.